process to other process while switching. It is saving certain information related to the process which is from which it is switching. That is called as a context data, context switching and context data. Also, you have IO status information. So, in case if there are certain resources are needed, of course, there are need of resources because memory also a resource. So, whenever you need certain resources and also the peripherals, the relevant information will be stored in the IO status. And accounting information means how much data you've used and what is the cost of it. Means as the memory usage or the time, how much time you have utilized. You can also have certain information related to the process which is going to. So this we call it as a accounting information. So we could see this is your process control block. Okay? It's a simplified diagram. In short, we call it as a PCB. So PCB is nothing but process control block. You when the process is created, you're going to you're going to have all these informations in uh, the data structure on the memory. Okay. So, yeah, as I have already explained, the same thing is given over here. So, process is nothing but a set of instructions. When a process is created, it is stored in the main memory, in a buffer or queue or a ready list, whatever you call. Okay. So, a process given with a particular unique ID will be identifier because I need to know that I can trace the process unless and until I delete that process. There are certain functions which is managed by the operating system like file creation, process creation, process deletion, etc. etc. Okay. So when a process created, there will be a unique identifier associated with the process so that I can distinguish it from the other process. And you have a state of information. That is, as I said, whether it is executing or blocking or any other. Then the priority level, program counter, so memory pointer to the program code and the data associated with the process, and context data. So they are present in registers in the processor while the process is executing. So certain information, return address, etc. So IO information and accounting information. Okay. So this I already explained. Okay, let us see an example of memory layout. So when a process is created, the process is written in the main memory. There is a memory wherein you are going to have the set of process. So this is a simple layout of a process. Suppose I have a process A, process B, and the process C. Okay. Let us say my program counter is having the address of 8000, which means it is pointing to process B as per this simple diagram. And here there is a dispatcher. So what is the role of a dispatcher? So dispatcher is the one that is handling which process is going to get the processor. Okay. So this will function based on the scheduling algorithm you have it, right? So the dispatcher will handle the various So depending upon the so many process, which process is getting the processor time. Okay, so that is decided by the scheduler, and dispatcher will dispatch it. Means it is giving the process to the for the execution. Means it goes to the running. Okay. So as we know that program counter points to the address of the current instruction of the process. Okay. Let us say this is what is pointed over here. So, and as we can see that your process A starting address with 5000, process B 8000, and process C 12,000. So let us say this is what is given in the example. Yeah. So a process is having set of instructions. So as it was mentioned in the previous diagram, you have some number of instructions given in these address for process A, and this is process B and the process C. So this memory list, you call it as a trace of that process, set of memory list, this address. I'm sorry. So this is called as a trace of that. This is the trace of the process A. Okay. So now, since we are handling multiprocessing, say I'm according to whatever the scheduling algorithm you have it, the process can switch from one to the other, right? So whenever I'm switching from one to the other, there is something like that there is a switching time. So that during that time, you say the context, that is the relevant information about the process in the process control block or wherever, that is there is a temporary memory allocated to that particular process. Okay. So from this diagram what you can understand is, supposing started with the process A. After a timeout, supposing I have a round robin sort of scheduling, I am given a specific amount of time for every process. Correct. Whether I complete the entire set of instruction or not, it is immaterial. In between, depending upon the timeout trigger or an interrupt, it switches from one to the other. So as we can notice here, there is a timeout, and this is the uh, dispatching time, wherein you save the information related to the particular process. Means I need to come back. If I go through here, so this is the address 5005 is the address. Till there I have executed, and there is a timeout here, and this is my return address. Maybe depending upon the when I am going to get back my execution time, right? So this address need to be saved, as well as some of the if there are certain information in the accumulator also need to be saved. So this is your dispatching execution given with the address 100 and so, and it will switch to the process B, and maybe let us assume that process B needs some input output, some resources. So when the process B needs a resource, again there is a switching because it goes to blocked. So process B goes to blocked in between the timeout period. You can notice that. Okay, whatever. There is an IO request, of course. This goes to the block, and there is a context saving. It needs to go to the process C. So start executing the process C. Hopefully there are no IO resources uh, expected for this particular process, and there is a after the timeout there is a switching again, and it goes back to process A, assuming that process B has not finished its IO process. It is going to continue with the IO process, and it goes back to the process A, and after the timeout, then it will go to the process C again. I mean, this is a random example shown. Maybe will get a more clarity with this particular diagram. So this color shows the running and the ready and blocked. Okay. So process A is running, and after timeout, there is a dispatcher. Process B start running. In between there is an IO request. It gets blocked, and there is a context switching. Goes to process C, and after timeout, and there is a dispatcher. It will go to process A since this has not finished, and after timeout, there is a dispatching, and continue with the process C, assuming process B has not finished its IO. So once it finished the IO operation, it will come back to the ready list. From there, you can pick the particular process for running. I hope you got this very simple. It's a same way as how we execute the subroutines or the. I mean, here everything is a functions, and they need to be given with this particular amount of time for the execution. Okay, this is just to show the, I mean, whatever I have explained, how it is going to get the processor time with the combination of dispatching and getting the processor time for run. Okay. Yeah. So now let us see how the process is going to get, created. Process creation. So when a process is created, the operating system builds the data structure, so which is used to manage the process. Okay. So we need to manage this particular process. So the relevant information as I have given in the initial slide, the various information are getting added with the process, which are stored in the PCB, that is process control block. Okay. So the data structure that are used to manage the process and allocates address space in the main memory to the process. It reserves a memory. So what is the space needed for the particular process? Okay. So in a batch environment, a process is created in response to the submission of a job. So when a process is, I mean, you call it as a job or the process. Whenever the process is, whenever it is, you find that there is a need. Of course, the the process is created depending upon the. I mean, anything you call it as a process. Like, I want to get some data or accessing the data or anything. So you have a different environment for the process creation. I mean, different set of environment which we put it in the operating system. In a batch environment, the simple sequential way of. An interactive environment process created when a new user attempts to log in something. Whenever you try to log in with, say, it's a like, in a simple way, I can say I am using any a mail system. There will be when I want to log in, like, it is something like there is a process creation. So it is when I log out, in the sense I'm going out of. So those are also called as a, I mean, it's a part of the process. I mean, it is a process. May also create a process on behalf of an application. You can have, I mean, what I mean here is, in what all the situations you are going to get the process create. Okay. So reasons for process creation. This is most important. So the first one, as I said, what do you mean by batch? The operating system is provided with the batch job control stream. So you will have some sort of anything which is there in the disk. Uh, so whenever you want to access that information from the memory, okay, it will read the particular set of sequence of the particular process, I mean the job, to control the commands. Similarly, you have interactive login. So a user at a terminal logs onto the system, as I have just mentioned an example. And also the process gets created to perform a function on behalf of a user program, anything. Okay. And there is also a something like spawning, in the sense you want to send the whatever the data from main memory to the second memory, so that you can have some sort of a modular, I mean, multiple program need to be run. So to have certain parallelism in the uh, operating system. So there also you can have, I mean, the reasons for the creation of the process. We have got a number of reasons for the process termination. I'm not going to explain these things. Maybe simple thing we can say that uh, we are going to delete the process deletion. So we have not able to see the one. Something like whenever timeout expires, when the process has timed out. So you have some certain interrupt. It has completed its time, then you can terminate the process. Or you try to use some certain memory and which is not available. Something like these are all called as an exceptions. It's a different exception handling also part of this, through which you're going to terminate the process. So you're trying to violate the memory violation, or you try to access a memory which is protected or privileged. You try to do that. There is a protection error, or divide by zero. It's an arithmetic error, or time overrun, or there will be some input output failures. You try to access some input output which uh, through which there could be some error, and because of which the process gets terminated. Maybe you're trying to have some instruction which is not available, invalid instruction you're trying to put it, so through which there could be a termination, so etc. I mean, there are a number of reasons listed here because of which the process gets terminated. Maybe these are all familiar to us since we have studied in the various exceptions or the interrupt handling, the similar, exactly in the same way. We're going to have various reasons for process termination. Yeah. So let us start with the simple two-state process model. A simple model of process. So in the beginning itself, I have just mentioned when a process is created, straight away we put it in the ready list. Nothing but you call it as they are not running. In very basic way, I can say there is a process not running or run. Okay, so not running process when it is dispatched means getting the processor time. Okay, start running. If it is there is any timeout or you put some pause, it will go back to the ready list. If it has finished, it will exit. Okay, so this is your queuing diagram. You put it in the ready list depending upon the, say suppose in you have a first in first out. These are all the various algorithm which will decide the allocation or assigning the process for the execution. So you have a queue, a ready queue. The dispatcher will dispatch the particular process based on the first in first out or a last in first out or whatever, or maybe highest priority process or the process which is having the shortest time for the execution. It will pre-calculate the process which consume less time for the execution. So based on the whatever algorithm you decide, it is assigning the process for the execution. Okay, so this is your queuing diagram in a two-state model. So now, okay, so there are certain limitations of two-state model. Let us see. I mean, some process in not running state are ready to execute, while others are blocked. What I mean here is, if a particular process is blocked due to certain need of an IO, right? Then you may not be able to put it back in the non not running state because it get mixed up. So you must have not given the particular algorithm to decide on what basis it should be given a chance for the execution next, right? So whenever there are blocking due to IO need, so you can have certain one more another extra state to put it. Okay, so this using a single queue, the dispatcher could not just select the process. So based on the see what happens is if you look at this the queue, so I'm allocating, assigning the process for for running, and the process which is going to get blocked, maybe I'll put it back right in the not running state in the queue. So it will go back, and the next one will get a chance for the execution. Likewise, it goes on. So depending upon the time taken for the IO process, still it may put up. It could be a hurdle again for the this particular queue. So better to go for another state because the dispatcher need to scan the entire queue for getting. So it is a time consuming process. Instead, we can have another state called as a block. Okay. So from two state model, we went to the three-state model wherein you have a ready, running, and the blocked. It's a very simple way of showing the process state diagram. So there will be a, but we've given the additional thing over here. This is new and the exit. Okay. So new is the process has been created but hasn't yet got admission in the ready queue. It is just created. It is yet to load in the main memory. That's what is the meaning. Okay. Ready is this is there in the main memory submitted for execution. All resources are assigned to it except the CPU. Please note. So whenever I'm getting the CPU means it is running. Okay. So the process which is running is on the CPU. Then I have a blocked state. So blocked is due to some IO need, the particular process which is running may shift to the blocked state. Means it's waiting for an event to come back to the um, main program. I mean to the running. Then the exit. So this is just a normal way of termination or abnormal. Abnormal in the sense due to some erroneous conditions. So there is a chances of terminating a process. Something like I try to do control or delete in case if there are some error occurs. This is what we do it. Okay. So this is just showing the different states of the process. Yeah. So not only the process states, we need to know the transition as well, the various transition in the process. So we can see that as we have seen in the previous slide, what is new state, ready, running, exit, blocked. Okay. So probably we put in any of the references, you find this way. The process state diagram is shown in the three-state model. Ready, running, and blocked. Okay. So you have a new state. This is going to load in the main program. It's admit to the ready queue. It is admitting in the ready queue. So once the processor, depending upon the algorithm you have it, it dispatches for running. Okay. And as we have seen in one of the example, when the timeout occurs, it goes back to the ready list because it has not yet finished. So it may get its turn maybe some other time. Okay. So it is going to get the time later. So it is after the timeout, this is a transition which we have shown. It goes to the ready and a particular process, if it is waiting for an event, it could be any event, something like a semaphore or a mutex or any IOs, anything. So if it is waiting, it will go to the block. We are going to see the various kernel objects through which you are going to push it. I mean, there is a switching happens between the various process. Okay. So running process goes to blocked, supposing it is waiting for a particular event. And whenever the event occurs, please remember, please note that it is not going back to the running. Through the ready only, it is getting the running state. Please try to understand. Uh, when a process is created, just created, it is in the new and when it loads having certain attributes related to the process, it's will be there in the ready list means it is going to get the processor time for the execution. Fine. So once the process getting a chance, the dispatcher will dispatch, means the process is executing or running. Whenever the timeout occurs, because maybe you stipulated time is reserved for every process in case, even otherwise, if you don't assign any particular algorithm for the execution, there will be a key switching between the process. Of course, it has to be. Otherwise, there is no point in saying that there is a multi-processing or multitasking. So, the process which is running, once the timeout occurs, it goes to the ready, or the process waiting for an event goes to the blocked. Okay. So whenever the event occurs, means I need not block anymore. It will come back to the ready list. What I mean here is, even though the event occurs, whatever the event I am trying to, I cannot come back straight away to the running. Please remember that. So normally people do that mistake while writing any program. It does no way. I mean, it is going through the ready and running. Okay. Yeah. So once you are done with the process, it will go to the exit. Okay. Yeah, I have already explained this. So now this is your queuing diagram for the process execution. So the three-state model, whatever the ready list, running, and the blocked. Okay. So this gives the clarity on how the various process are getting the processor time for the execution. As I've shown, there is an admit and the queue, and there is a dispatcher. So when you finish, it will release, or else if timeout, it goes to the ready queue, and if waiting for an event, goes to the blocked queue. So what happens is, whenever we have a multi-processing, there are multiple processes in a queue, right? There are multiple process. So the process going to the blocked queue, okay, either they are terminated or placed in the ready queue or the blocked queue, depending upon the circumstances, depending upon the particular process which is executing. So when the event occurs, all the process in the blocked queue waiting for that event are moved to the ready queue, right? Suppose say I have three process, for example, as I have given in the initial slide, that process A, B, C. Process A, I'm sorry. After timeout, it goes to the ready, right? Then process B gets a chance for the execution, and process B is waiting for an event. It goes to the blocked. Fine, it goes to the blocked, and since B is going to the blocked queue, it is not at come back to the ready. Since I have process A, B, C, right? A is done, B is pushed. Now I am having C here. C get a chance for the execution. Process C starts executing. After its timeout, it will put it back in the ready queue, right? If you imagine your ready queue, so now in my ready list, process A, B, C, right? Process A, B, C. A, I have, after timeout, it has come back. Process B in the blocked queue, process C here, right? So again, process A will get a chance for the execution. After timeout, process C gets a chance for the execution, provided the IO operation has not been completed. Correct. So there is a this list shows how the various processes are getting handled for dispatching or execution. Okay. So in a blocking queue, you can see that there are process. Suppose in this example I have given only 3. Suppose there are more process. Whichever the process waiting for an event are loaded in the blocked queue, and suppose you imagine that you get a I mean there is if there is whatever the event it is waiting, you if the event occurs, it will come back to the ready queue, right? It will come back to the ready queue. So as soon as the event occurs, it goes to the ready queue. This is what is happening in the particular single blocked queue. Single block queue. Now we have another way of putting the this queue listing. Supposing I have a queue, that is blocked queue for each event. Okay, so event 1, waiting for event 1, event 2, event 3, etc. So the process which is released, no issues. The process which is has come back after the timeout, it will put it back in the ready queue again. But this is the queuing diagram showing multiple blocked queues. Showing the multiple blocked queues. So you have for block 1, I mean 1, 2, 3, etc. So the this alternate solution could give you lesser time for the searching for the process. Okay, so as soon as the event 1 occurs, it will come back to the ready list. So for event 2 queue, you have this, I mean, if the process which is waiting for the event, the different events, you categorize or distribute for the different event as a separate, which will simplify your job in dispatching the various process for execution. So this is a multiple blocked queues. So multiple block queues. So yeah, to elaborate more on the whatever the detailing we have given, the diagram. So the operating system must scan the entire block queue, right? The operating system must scan the entire block queue when an event occurs, searching for those processes waiting on that event. Which process is waiting for an event, right? So that needs to be taken care by the operating system. So suppose you consider you have if it's a small operating system, no issues. If there is a long or the large OS, and there could be a more number of events, in that case, would be more efficient to have a multiple number of queues, right? So in the previous diagram I have shown, here I have only a single queuing system for the blocked. So if there are multiple events and multiple process are put up in the queue, there it is very difficult to trace for the OS to I mean, to push it back to the ready queue, because it needs to scan the entire queue. So here we can see that we have separated for each. So the flaws here, processor is much faster, and please note that why we went for this, because we generally know that the processor execution time is much higher than your IO, right? IO execution is much slower compared to your processor execution, of course. So the blocked queue is due to your IO operations. Right? Blocking queue is due to your IO related stuff. And the as we know that the ready queue and the running occurs due to your I mean processor executes very quite fast, and it needs to scan the block queue. As we know that the processor's execution time is quite faster than the IO. It's common for all of the processor in main memory to be waiting for an IO. Correct. So means IO could be a main memory also. Supposing I want to expand the memory, definitely the cost will be increased. You're going to increase the cost because as I add the memory into the system, definitely the cost will increase, which I don't want to have. So the solution could be you can try to go for some sort of a swapping. Okay, swapping in the sense, consider what we mean here, the swapping. Consider that a particular process need an IO and it is put up in the blocked queue. Blocked queue is also part of your main memory, correct? So it is part of the main memory, and it is waiting in the particular memory. Means it is waiting for an event. So until the event occurs, it is still put up in the main memory. So I may be underutilizing my the memory. So the solution could be, if a particular process waiting in the block queue for a longer time, you can push it to the secondary memory so that there is a vacancy created so that I can bring another process onto the system. Okay, so that you call it as a you sort of a use. I mean, the process waiting for a longer time, instead of having that process in the main memory. So if I keep on increase the size of the memory, definitely it will increase the cost of the system. Instead, temporarily you push it onto the secondary memory. Okay, so that there is a vacancy created so that you can bring another process onto the system, and depending upon uh, the uh, the availability of the processor and as per your algorithm, it gets a chance for the execution. And once the event occurs for the process which you have pushed onto the secondary memory, maybe you can bring it back, okay, provided there is a space. Okay. So that with that idea, we could see another model, okay, with the additional state which you call it as a suspend. So this is your 6-state process model. This is the 6-state process model. So we have already seen there is a 5-state: new, ready, running, exit, and the block. In simple, ready, running, blocked. Apart from which, we've shown the new and the exit. So these already I have explained. Okay, what is uh, the process in the ready? What do you mean by process in the running and the block? This is the additional state which you have included, called as a suspend state. Okay, so even though I give a different queue for the different events, right? To explain in a better way, for example, this One, say you have segregated to the events. Please know that whenever the event occurs, it needs to search. The operating system needs to search which process for waiting for an event, right? Once that is done, it will put it back into the ready queue. So here the process waiting for a longer time for an event to occur can be pushed in the secondary memory. Okay. Yeah. So this is your 6-state process model. You can see here from the blocked, as I have just mentioned, blocked state is the process are waiting for the event, for an event to occur. The process who is waiting for an event to occur, and the process is waiting for a longer time for an event to occur. Instead of putting in the main memory, you push it to the secondary memory, nothing but your suspend state. Okay, it's a suspend, and the transitions, I think you're familiar with this: release, timeout, event wait, event occurs. So here you're pushing the process from the block to from main to the secondary memory, and you can activate. You can call it as it is inactive, but it is not. It is just there. It's not finished. Please remember, I cannot exit that particular process. It is need to be given a chance for the execution, and if event occurs from suspend state, it will uh, put it back into the ready list provided there is a space. Okay, so activate and put it in the ready list. So when all of the processes in the main memory are in the blocked state, the operating system can suspend one process by putting it in the suspend state by transferring it to the secondary memory, nothing but your disk. Okay, this is what is done in the operating system, and we call it as a 6-state process model. Yeah, so adding to it, we can have the one more, that is the suspend state. We can put it as ready suspend and blocked suspend. So there are when we need to know the difference between these two. Here you could see there are 7 states. This is a 7-state process model. I mean, you have a 2 suspended state. One is a ready blocked suspend and another ready suspend. The difference, simple difference is only this. The blocked suspend is the process in the secondary memory, waiting for an event. Okay, waiting for an event. And ready suspend is, it's also, suspend is, of course, it is in a secondary memory, but it is available for the execution, okay, as soon as it is loaded in the ready list. Okay, as soon as it is loaded in the, so this is your secondary memory. So as soon as you get a chance, you can put it in the ready. But here we could see that blocked, it will go to the blocked suspend because it is still waiting for an event, and if the event occurs, it goes to the ready suspend. From there it get activated and come back to the ready, and provided if there is any timeout or something, it will go back to the suspend. Okay. So in the same way from ready, locked suspend, we can have ready suspend and blocked suspend. Okay, addition to this. So this is your state model for the process. Yeah, I went on with the process diagram. I hope there are no queries. In case if there are, please. Yeah, this is the explanation for the transition diagram. More or less theory you can. Yeah. So we have given the additional state, which is suspend state. We need to know the reasons for the process suspension. Why we are going for the process suspension. There are a number of reasons listed here. One is swapping. The OS need to release sufficient main memory to bring a new process, which I have already mentioned, right? So maybe there are no space for the new process because the process is taking longer time for IO, and you can, because of which you can temporarily push back to the secondary. And there could be other operating system reason. The operating system may suspend a background or utility process. So I've already explained what is the utility process. There are certain utility process. So that is suspended, causing a problem. So maybe because of which you can have the suspend state. Third reason could be interactive user request. A user may wish to suspend execution of a program. Maybe for when you do some certain debugging. Okay, so maybe you're single stepping. In which case, I want to suspend. I want to temporarily push it and check. This is sort of a debugging process, which you can have a process suspension. Then timing. A process may be executed periodically and may be suspended while waiting for the next time interval, which I have shown, right? Whenever there is a timeout. So whenever the timeout occurs, it is suspended. In the sense, you call it as a blocked. So blocked, maybe you can, uh, but you should have a clarity in the blocked state and the suspend state. Blocked state is still it is in the main memory. Suspend state is it is in the secondary memory, the blocked process. Okay. Another reason could be parent process request. A parent process may wish to suspend execution of the dissident or to examine or modify the suspended process. Some sort of you want to. So maybe you want to uh, suspend a process by your main program. In the main program itself, it is asking for suspending the particular process. Okay. So there are different reasons through which you can suspend the process. Now let us see the characteristics of the suspended process. I have highlighted here, since the suspended process in the secondary memory, it is not immediately available, right? It is not immediately available for execution because it needs to bring back to the main memory for the execution. Yeah, this is one of the the most important characteristics of the suspended process. The next is process may or may not be waiting for an event, right? It may not be, it is waiting for an event or may not. So this block condition is independent of suspend condition. Okay. And the next characteristic is was placed in a suspended state by an agent. Okay. Through some agent it has put up in the suspended state, either itself or through a parent process or operating system must have been. Yeah. Hello. Any queries? Hello. Somebody said something. I couldn't hear. Yeah. So these are the some of the characteristics of the suspended process. It's more clear. And there is a process control block. So process control block. We have seen the beginning itself. There is a process control block, a simplified diagram having process ID, and there is a program counter and context memory and other parameters. Okay, so state. So there is a process control block which contains the various information relevant to the process, like program counter, priority, etc., etc. So how the process is, we can see in the memory, process in the memory. So you have a process ABC. See, there is a kernel space, and then you have an operating system, and we can see that process. There is an interpreter, process B, and you have a free memory, free space, etc. How you can visualize the process in the memory. So this is your single process layout, and you have a text, data, heap, stack. Anyway, these terms we are going to see in detail maybe in later sessions. So this is just to show a simple memory layout of a program. Okay. You have a main program. In main program, you have some variables assigned. For example, here I am having x, y, and sum, and x and y is given some data, and you say when I say sum is, these are all like variables reserved with some certain integer, means that much space need to be reserved for these variables, and when I add it, it will go to the sum, and so this is your the function for add. Okay, int a b total, and total is whatever, uh, say a plus b plus tax, return total. So initial value will be considered as a tax, which is 0. So this is what, it's a random example shown how your memory layout looks like. You have a process. Yeah. Oh yeah, this you can refer the stallings for the whatever the data or the relevant information I have shown in this particular uh, slides. There are no doubts. I'll move on to the next. Yeah, if you have got any doubts regarding the process which I have explained, please raise. Otherwise, I'll go to the next topic. Anything? I went on. I did not ask you in between anything, any doubts you have. Any doubts? It's more or less theory. I think you can have a look.
No, ma'am, no doubts.
So uh, the process definition we have seen. Now we just see the process description. Okay. So to come back from the whatever the topic we started with, so operating system need to manage the multiple process or as well as the multiple process in the sense it need to manage various resources, resource management. That is one of the service provided by the operating system. So resource management is nothing but it needs to uh, service various or to control the various events through the event. Event is nothing but it could be a timing trigger or it could be anything it is in need. You just put a signal or a message, anything. So these are all called as an event. Okay. So that you get to know that okay there is something or somebody is waiting. Something like I want to enter into the room, either I bell or I knock. I knock the door. Same way. So knocking the door or bell, pressing the bell is it's an event. I mean, the processor who is sitting inside, he should know that okay, there is somebody which is in need of my service. Okay, that way I can put it. Yeah. So the operating system controls events within the computer system. So there will be a scheduler, and the scheduler and dispatcher will take care of uh, scheduling the different process. Please note that one more book I have uploaded maybe yesterday also, that is Quingly. You just go through it to have clarity on dispatching, what is the role of scheduler, etc. So more or less theory, you can just go through that 1 or 2 chapters on that. You'll get a better idea of what is a dispatcher. Okay, so that book explains in a very clear way. Please do that. So I just assume that you know about what is a scheduler and what is a dispatcher. I just go on. Okay. So if you see that process needs to manage the various resources, including a processor also one of the resource. That's what we consider here. If you list the various resources, processor, IOs, main memory. Maybe I have to identify, you put processor and IO separate and the main memory. Altogether, I can consider these are the resources, computer resources. And this is your memory section. So process, which is when it's created, it will be in sort of a virtual memory, in a virtual memory. It's a part of your main memory. So you have various processes, P1, P2, etc. Okay. So this is what we can visualize. So the P1, now it's showing that processor means currently it is running. Okay. So I may need all these resources, main memory. Okay. So this also need a IO and the main memory, because once it is allocated, I cannot show more than one process in a single processor system for getting executed, which is impossible. Okay, please try to understand that. So this is your control structure, operating system control structures. Uh, to manage process and resources, the operating system must have the current status of each process and the resource. What is my current state? Whether it is so here, this is showing the general structure of the operating system control. Okay, so you have memory and devices and the files and the process. So memory blocks, IO blocks, file. Okay, whatever the task you have, memory task, you're segregating the memory related task. Just a second. So these are all the tasks we have for the I can say for memory task and the IO task, file task, and for the process. So you have the various. I mean, these are the listed process one, two, etc. Okay. So this is the process image. Okay. So this is called as a process. So the operating system constructs and maintains a tables of information about each entity. Okay. For any entity, you call it as an entity, could be any. So it needs to, there should be some database. I mean, it needs to know that which process is created and whether it is having the highest priority or the lowest priority or the middle priority, or whether it is currently running, or whether it has timeout and put it back in the ready. All this, I mean, your return address, etc., etc. So every information must be uh, located in a particular place, which is your process control block. So the memory tables are used to keep track of both main memory and the secondary memory. Okay, which is normally we call it as this is the real memory and this is the virtual memory. And processes are maintained on the secondary memory using some sort of a virtual memory or simple swapping mechanism. You can swap it. I can save somewhere in the hard disk and I can get it whenever I want to run the system. I mean, run the process. The memory table information. So you have, I mean, it should maintain that. So the allocation of main memory to process, allocation of secondary memory, and any protection attributes or any information needed to manage virtual memory. All these informations are getting loaded in the memory table. So you have IO tables. So IO tables and the file tables and the process tables so that you can manage the process. These are all the information related to the multiple process which are created. Okay. So you have a process control structure. Maybe we'll stop here. I'll continue with this maybe from in the next class. Uh, if you want to ask anything, you please ask, or we'll summarize. So today we've seen the what is a process. I mean, how the process looks like, the process as an entity, and the process state diagram, the various process states. Started with the two state, a simple structure, and you have a three state model having inclusion of the block reason for including the blocked state, skewing diagram, and we went for it's a three state nothing but you have a additional two states, the process created and the released, new and released five state altogether. Then you have added another state called as a suspend state, became a six state model. The reason for going for the suspend state, and you subdivide the suspend state into the ready suspend and the block suspend. Please try to understand the difference between these two. Okay, suspend state is which is the process which is in the secondary memory, and what is the difference between the ready suspend and the block suspend. Okay, so yeah, so we've seen the state models of process, and started with the process control. I mean, uh, how, I mean, what are the informations are needed so that I can properly handle the various processes in the multiprocessing environment. So since it's a multiprocessing environment, definitely we need to keep a track of which process is currently executing and which process, and what are the processes are in the ready and what are the processes are in the blocked state, because somebody there should handle these so that you can get a smooth, I mean, ultimately we need to make use of the efficient utilization of the processor. That should be our goal while designing any operating system. So any operating system will have a particular objective apart from whatever I've initially started with, that is to make the user getting ease in the functioning of the system. Not only that, uh, even though the performance of the system is given, I want to efficiently make use of that. Okay, so with that intention, the various algorithms are put up, and still there are so many flaws again, and they may look into how we can avoid, I mean, I can make it in a better or efficient way of using the processor time. Okay, not only processor as well as the various resource handling. Maybe we in the particular course we are not focusing on the additional, I mean, other resource management like IOs, but we are looking on only the processor as a resource, and that too we are discussing on the uniprocessor environment. Okay, if you have got any doubts, you please ask, otherwise we'll leave. Any doubts? Yeah.
No, ma'am.
Okay, so only you are responding. What about others? I could see the less number of attendance. Anyway, it's up to you.
Ma'am, there are OTs of different companies today.
Okay. Okay, then we'll leave. Yeah.